Hey everybody, welcome back to Question Field, the place where you ask the questions and we field them. And for the first time, we're not lying about that. We are actually working off of a user-submitted question. I'm Brian. I'm joined, of course, by Campbell, and we have a guest today.
Hello.
Yes, we're joined by James from last episode. We're picking up basically where we were last time. But just as a refresher, here is our question from Andrew. Andrew, thank you again for sending your question in. All right, and this is what he said, all right? Just started listening to the latest episode of your pod, and the topic of dimensions got me thinking about something I would love to hear your perspective on. I'm a mechanical and manufacturing engineer. One thing that has always mesmerized me is resolution of measurement and error calculations in general. It'd be great to hear how these concepts fit into the theoretical side of physics. So that came from Andrew. Thank you, Andrew. And again, thank you, James, for being here, for joining us.
You're very welcome. It's great to be here.
Yeah, thanks, James. Last time we were building up to answering this question in the context of particle physics and specifically your research, James. And we talked about proton structure and parton distribution functions, how you might go about looking for new physics that goes beyond the standard model of particle physics by kind of adding these interactions, these terms in your equations, and then seeing if the resulting theory is better explains the data. Is that a fair summation, James?
Yeah, I think so. Yeah.
Okay, cool. I guess to get to the crux of the matter, in order to kind of figure out like how good of a picture we have that is explaining the data, I guess we need to have some idea of the errors and the sort of degree of certainty that we have on our observations and theoretical predictions. Is that fair to say?
Yeah, that's exactly right. Yes, yeah, absolutely.
Right. And so how does this come into your research?
Well, so we're specifically concerned with these functions, these parton distribution functions, which I guess we were talking about last time. But the key thing that we want to know about these functions is how precisely can we know these functions? We need to have some sort of error bars on the functions because we are inferring them from fits to data. And
just to jump in real quick, so to recap, these functions told you like, given a certain energy and momentum of your protons, how likely is it that you're going to find some muon at a certain energy, or some quark or gluon shower, or something like that? What are the probabilities of finding certain products of the collision? Is that right?
Yeah, that's exactly right. It's the probability of ejecting something from the proton. Exactly.
Right.
So that then participates in some sort of like hard scattering reaction. Exactly. Cool. We, as we said last time, actually, they're inferred from fits to data. So we have this picture of the data that we get from the collider experiments, and we also have this theory prediction, which involves these functions and also involves some sort of hard scattering reaction. And we compare the two of them together, and we try to infer what the functions are. And of course, it's very important that when we actually infer the functions, we also have some sort of error propagated from the experiment. So obviously the experiment comes with some sort of error. There's lots of sources in the error, in the experimental error. They come from poor statistics, so not having enough collisions, they come from systematic errors. So things to do with like detector effects that have to be propagated as well. All of it taken care of by experimentalists and all packaged into essentially one big error bar on their measurements, often correlated between different measurements as well. So errors on one can affect errors on other measurements. So a lot of it is quite highly complicated statistics from that end. And then we take that data and we say, okay, well, can we infer the function? And also what uncertainty can we infer on this function as well? And it's obviously important to have a measurement of what the uncertainty is like, because if we then take this function and we use it to predict something else, like predict the effect of another proton-proton collision, we want to know like what can we expect and what kind of error can we expect on the resulting prediction. And it's particularly important to know these functions very well when we're doing the kind of thing that I do, which is looking at new physics effects, because you might reasonably say, okay, well we need to have a precise knowledge of these functions before we can even start hunting for new physics, which we're going to have even less of a precise knowledge about. So we need to make sure all of our standard model predictions are really, really good before we start worrying about new physics first. So it's a very important issue in terms of how do we propagate the experimental uncertainty onto these functions?
Because I guess the in order to say that you've made a discovery in physics, right? You have some sort of likelihood that, given the data that you observe, the null hypothesis, if you like, is correct, right? The sort of in this case would be the standard model. Given the data that we predict, that we observe, sorry, what's the probability that the standard model still remains true? This might be, I guess, the kind of question that you would ask in a sort of statistical test.
Yeah, exactly. That's the sort of thing that we might propose if we were doing a hypothesis test for new physics. Exactly.
And there's a sort of cutoff, right? If you see some sort of probability which is very, very, very small, then you can, and it has to be particularly, it has to be smaller than a particular value. Then you can say, okay, well, we've made a discovery. This is definitely now good enough to say that there's new physics here.
That's exactly right. Yeah. So, and the threshold for that in particle physics is what's called 5 sigma, which is 5 standard deviations away from the mean. If you approximate your distribution as like a normal distribution, and if your probability is further, like if your event is less likely than that, then you can say pretty securely that this is something that you can be confident is not just statistical fluctuation.
And I guess the sort of error that you've propagated through from the experiment to the Parton distribution function that you calculate, that plays a role in determining your confidence level, right?
Exactly. Because, of course, the Parton distributions themselves are then used as an ingredient for other theoretical predictions. So they were used in the discovery of the Higgs, for example, in making the predictions for Higgs. They were inferred from some data and used for the Higgs discovery later on. So, the error on those will form a part of the overall picture of the error that is put on the final predictions.
So I guess to maybe sensationalize a little bit or sell the idea of this episode, this is kind of like the heart of making discoveries in modern day particle physics. You really need to get a good handle on this in order to say that you're finding new physics.
Yeah, absolutely. Yeah. Of course, it is just to desensationalize. I guess it's only one source of error.
Course.
There are, of course, many other sources of error, both on the side of theory and the side of experiment as well. Another great example is from the theory side of things is that when we do the predictions for the hard scattering cross section, so the thing that I described as like classical billiard balls, that they also have quantum corrections in those, and we can't calculate all of the quantum corrections. So there are some that are missing. So people have to estimate, what kind of uncertainty can we expect from the ones that are missing? So they're called missing higher order uncertainty effects. So that's also an ingredient that goes into the theoretical side. That along with these Parton distribution errors, there's errors from the hadronization effects, as I was talking about before, and things like that. So errors appear all the time, but and certainly the putting them all together is no easy task. But but it's something that you have to do if you're going to make good predictions, man.
Yeah. I mean, it sounds incredibly complicated to make sure that you're accounting for all of the sources of error and that you're combining them correctly. And as you're going to talk about, sort of propagating that through the calculations. So, okay, so what sort of methods for? So you've got these experimental errors that you're sort of given by the experimentalists and by the data that you're observing. I guess because you said that there was sort of if there aren't enough data points, then that sort of comes with some inherent uncertainty associated with that data. So okay, and you want to then come up with some uncertainty on the Parton distribution function at the end of the day. What's the kind of process from getting from A to B there?
Well, it depends on how you fit the Parton distributions, basically. So there are lots of competing approaches. There are kind of like 3 main collaborations that do this kind of fitting. So from the collaboration that I work with, which is the NMPDF collaboration, so which stands for Neural Network Parton Distribution Functions, which is to do with the way that we parameterize these functions. The name comes from the fact that we use a neural network to model the functions. That's actually, just to take a step back for a second, that is actually an important thing to mention before we can go anywhere. When you're trying to fit functions in physics, functions are like these nice smooth continuous things, but you only have finite amounts of data. You might have thousands and thousands of data points, but you're trying to infer information about something that potentially has infinitely many degrees of freedom because it's a continuous thing. So how do you do it? Well, in physics we have to come up with some sort of way of modeling it. So we reduce the functional the freedom of the function to only a few parameters. And some people do this by modeling it like a polynomial or something like that. So there's some sort of like sum of power laws. But in the collaboration that I work with, we use neural networks instead. So the idea is that they are hopefully more flexible in terms of the way that you can do this kind of parameterization.
And surely, if you have the word neural network in your collaboration title, it's much better for funding, I imagine.
Yeah, absolutely. Yeah, and you say, we do quantum physics with neural networks, and you go, they throw money at you. Not really, though. Yeah. No, you need to say quantum. You need to say quantum computing, and then they'll throw money at you. But
True. We should talk, James, at some point.
So I always feel like the particle physics. So me and Campbell both obviously we work at Cambridge together, and the particle physics seminars I feel are always very underfunded compared to the quantum computing ones. So I'm always very very envious of but anyway, So to go back, we as I say we parameterize these functions with neural networks instead. So they've got a finite number of parameters, so they can be now fitted with the finite amounts of data that we have. So but it obviously restricts the form that the functions can take, but it's still sufficiently flexible, we believe, to accommodate the data. So those are the things that we want to come up with like errors on. We want to come up with errors on the neural network parameters and say what is the uncertainty on these parameters from the data. And the typical way that the way that our collaboration deals with it is something called the Monte Carlo replica method. This comes from the idea that if you give me an experimental measurement and you give me some sort of uncertainty on it, this is really the idea of the Monte Carlo replica method says, what in some other universe had someone else made the measurement, then it would be like maybe I can pick what the measurement would have been, what the central value of the measurement would have been according to the distribution that this is telling me. So so I should fluctuate around the real world experimental value by throwing the dice and saying, okay, let's plop another point, close to that, according to the number of standard deviations we have. So perhaps points closer to the real experimental value will get picked more often. Further away, they'll get picked less frequently. We imagine, what would have happened in these alternative universes, and we generate a big selection of samples of these to kind of supposed to spread out, 100 different universes or 1,000 different universes where the measurement was repeated, but we got different results, but they're all fairly consistent with one another, and the real world measurement is the one that's governing the statistics of these measurements. So for each of these these fake pieces of data, so the ones that we've generated ourselves, we then say, okay, let's fit the Poisson distributions perfectly to each of these fake pieces of data. Okay, so we perform our fitting method. We do a minimization that gets the best fit parameters for each of the different points for each of the different universes, and we get a big spread of resulting Poisson distributions. And from that spread of Poisson distributions, we then say, okay, right, well, from that we can infer some sort of statistics on the Poisson distributions. We can infer some error bars. We look at the whole ensemble and the group of them together, and then we can get the statistics that we want. And this is supposed to be a very flexible method in terms of error propagation, because it's very intuitive to understand. It's very easy to implement, and it also means that you can propagate errors that are not normally distributed errors as well. It's very standard in physics to have normal distributions. So bell-shaped kind of curves. But if your data is not necessarily normally distributed, it doesn't matter at all with this method. You still throw your dice, but you just throw it according to the other distribution that you're using, and you can still propagate the error correctly in that way. So that's the kind of the general method that is used by the collaboration that my supervisor works with.
So let me see if we both or if we're all on the same page here. So you're generating new data, these alternate universes where the data points might be quite close to the ones that you observe in real experiments, but sort of shifted by some random amount, maybe. And somehow that shifting is going to be maybe set by a distribution, probability distribution, which itself comes from the experimental errors of that, like the error bars around that measurement point. Is that correct?
That's exactly right. Yeah.
Okay. So that's how the sort of experimental error gets baked into this propagation thing that you're proposing.
Precisely. Yeah.
Cool. Okay. And then right. So So for each point, you shift the point a little bit, and if you do that for all of your data points, that gets you a new universe, and then you generate a whole bunch of universes, and then for each of those universes, you look at the parton distribution function that you can generate, and then and then you can look at the kind of average of those and the spread of those and that kind of thing.
Precisely, yeah, that's exactly what we do.
Cool. And that's Monte Carlo. What did you say that was? Sorry, Monte Carlo something or other?
So it's called the Monte Carlo replica method. Okay,
replicating the universe. Okay,
exactly.
Makes sense.
So the different samples you call replicas, and so you end up with like an ensemble of replicas. Yeah, exactly.
Wow, it kind of sounds like you're stepping into the Blade Runner universe. I don't know if you've seen that film.
I haven't. I know a bit about it though. Yeah, it's
creating these replicants.
We should call them replicants. Yeah.
That'd be fun. Yeah, and then you've got to have some sort of part of the maths which goes through and kills off the deviant replicants or something like that.
Well, you say that, but it's almost true sometimes. Like sometimes you get portraits that do have to be cut, and you say, this is not a realistic one. Anyway, So
fair. And so Monte Carlo is like this broad kind of suite of methods, right? Which is very useful in physics, isn't it?
Yes, that's exactly right. Yeah.
And I guess the kind of unifying thread in all of these methods is randomness. In some sense, you're kind of tossing coins and trying to sample from some underlying distribution, probability distribution. So I guess the one example that I've come across is estimating the value of pi. And so if you throw darts at a dartboard, which itself is inside a square, and you look at the ratio of darts that hit inside the circle of the dartboard and those that hit just in the square in general, that ratio is going to, well, no, that's not going to be true, is it? The ratio isn't going to approach pi, but it's going to approach 1 on pi, maybe. Is that, that's probably true, right? Yeah, the square's area divided by the circle's area.
Yeah.
Right, so that would be like a Monte Carlo method for estimating pi, right? You're sort of randomly throwing darts at a dartboard.
Yeah, exactly. This is exactly right. Yeah.
Cool. And so and the randomness comes in your case by these replica data points.
Precisely. Yeah.
Cool. Okay, and so that's a nice story. Does it? is it the complicating factors that you need to take into account?
There can be some problems with this method. Yes. So there are various other techniques that you can use instead to propagate errors. So and you can kind of benchmark these methods against one another and kind of see the kind of different distributions you get. Importantly, though, this is the case in general with statistics, which is the method is usually not wrong. It's your interpretation of the method that can lead to to misleading results sometimes. Not understanding the statistics you are doing can mean that sometimes you can get some strange results. So the Monte Carlo replica method, it sounds very reasonable and sounds like the sort of thing that you should always do because it sounds like, obviously this is going to work and this is going to definitely propagate errors correctly. But there are kind of other reasonable things that you could say, in terms of ways that you could actually propagate the errors. So another classic method of doing error propagation is using Bayesian methods instead. So Bayesian methods work on a slightly different kind of approach, where they work with you start with some sort of prior assumption about the distribution of your parameters in your model. So in terms of the parameters that parameterize the parton distributions, we might assume some prior knowledge of them and say, I reckon that they're about this, in between these kind of intervals, and we insert all these assumptions. Then we use this mathematical tool called Bayes' theorem, which tells us how the probabilities are updated according to observations of evidence. Okay, and you can use this to propagate errors as well. So you can use Bayes' theorem in this exact way to work out exactly how the errors should change. And here it's very clear where your kind of bias and assumptions have been injected. You inject it right from the beginning and say, this is what I expect. Before the experiment, this is what I thought, and this is what I get after the experiment, after I've seen some evidence. So this is another method that you might use to propagate errors as well. So using, as I say, Bayes' theorem. this is different from the Monte Carlo replica method, as it turns out. They don't necessarily give you the same results, and both sound like fairly reasonable things to be doing. So it can be
kind of annoying that they don't agree.
Exactly. Yeah. So you might expect that all statistics should give you exactly the same answers. But naturally, a good question to ask is okay, well, which one should we trust then? Which is the one that's a proper indication of kind of the error that we're expecting. And it's sometimes quite difficult to tell, to be honest. What the best thing to be doing is. You kind of need a proper appreciation of what you are going to use your statistics for. And typically in physics, Bayesian methods are preferred. The Bayesian methods are thought to be for most of the applications in physics, Bayesian methods are more suited in terms of the way that the way we actually conduct physics. In the general framework is you have some assumptions about your model, you update the assumptions according to experimental observation, and you get some inference on the final distribution of the parameters. And that is how physics works, really. So it is kind of like almost a mathematical simulation of what you're actually doing in terms of the experimental stuff. Monte Carlo is kind of a bit more abstract in terms of saying, we're just going to pick lots of different universes and fit lots of different things, and this seems also very reasonable, but it is not quite the same thing in terms of the actual in the way that the maths works out. One of the key problems actually with the Monte Carlo replica method is that sometimes your theory can't account for the universes that you have generated. And this is a big problem sometimes. So you can imagine, for example, that maybe let's imagine a very simple theory. So imagine that your theory is just maybe like a parabola or something. So like a curve that has a minimum, and it's describing a single data point. Okay, and that's our aim is to fit this single data point using my theory. And my theory, as I say, is just a parabola. As I vary the parameter, it changes the height of the parabola, and one height of the parabola is going to agree particularly well with the data or something. That's perhaps a very, very simple scenario. But you'll realize very quickly that, okay, but that parabola has a minimum value. Okay, it can't go smaller than a certain value, whatever value of the parameter I pick. Okay, if there is no way of getting a theory value which is smaller than the minimum of the parabola. Sure. So if we start off with our data and we generate loads of random universes around the data, it can be the case that the data falls below the minimum of the parabola in my fake universe. Even if the data was perfectly fine and consistent with the theory to start with, in terms of propagating the error, maybe in one of the fake universes I generate, I get a point that's below the minimum of the parabola. Okay. That's a bit of an issue now, because how do I fit that universe? What is the best fit value of the parameter in that universe? Well, you get the minimum of the parabola, you get the smallest value there, and you say, that's the best fit for that value. And this is a bit of a problem in terms of the distribution that you get as a result, because the distribution now starts piling up with the same point really being favored constantly by if we generate in lots and lots of the universes that I generate. So you can kind of end up getting a really strange spike in the kind of the distributions that you get, and it can look like your function a lot more certainly than you actually expecting to know it. So there's kind of this inherent problem with Monte Carlo when the theory is not really suited for the data that's being described, or the theory is maybe strongly restrained in certain directions or something. So Monte Carlo can have this kind of this problem.
So okay, let me see if I'm understanding correctly. Because I think I'm sort of a little fuzzy on how the particle physics case relates to this parabola example.
Yeah.
So in that particular case, the parameter that describes the model is just the height of that parabola.
The idea is that as I vary my parameter, the theory traces out a parabola basically.
I see. Okay.
Yeah.
Okay.
So for example, you might pick I don't know, the parabola might look like something like, I don't know, like the parabola might be x squared or something, and the theory parameter x corresponds to a theory like x equals 2 or something corresponds to a theory prediction of 4, and it's this correspondence between saying, oh, what's the model parameter is X, and the theory prediction corresponds to this parabola.
I see.
There will be one measured data value which is going to be a good fit for the parabola, for example. So it might be that the measured data takes the value, I don't know, like 16 or something, in which case the best fit value for the measured data is the 0.4, but we still want to propagate error from that measured data. So you still have to do this kind of Monte Carlo, like making lots of different universes things. If the measured data were say 1 instead, and maybe there's an uncertainty of, I don't know, 4 on it or something, then you might end up getting lots of things that fall beneath the smallest point on the parabola.
Right.
And this is where we get this problem that actually, you get lots of universes which we don't believe can be universes, basically. So really they should not be included in the Monte Carlo propagation. But yeah,
if I'm understanding correctly, this is the issue arises from effectively you're generating these replica universes by assuming some kind of distribution around the measured point, and that distribution is given to you only by the kind of measurement uncertainty, right? Should you not sort of build in the theory a little bit more into determining that distribution? I mean, should you just heavily penalize or set to 0 the probability of generating a replica universe that doesn't agree with the theory? Or is that assuming too much the theory? So you can say that you're going to cut out any replica universes where this is not the case. Unfortunately, this still doesn't actually solve the problem. So though it optimistically you might say that it does, but it's not quite, unfortunately. The problem is that you can the distribution that you get is still slightly distorted compared to the kind of distribution that you want. The main problem is that the behavior near the minimum, you still get like a pile up of like solutions that like near the minimum that are not quite reflecting the correct decay that you should be getting in the distribution. In fact, if you remove all of the replica universes, the thing that you get is, instead of getting a massive peak, you end up getting a trough where you should be getting like something that's a bit more smooth. So so the pile up is not quite correct in terms of the way that you're doing the sampling. So so you can say, okay, well, what if I just like weight the distribution a bit more towards the bottom? What if I alter the experimental distribution? At this point, you're now fiddling with the experimental data and saying, really, I expect the experimental data should not be a normal distribution anymore. I think it should be this distribution instead. You modify a little bit more to try and fill in the trough and try and get a nice distribution for your parameters. At this point, you can kind of fix things and get things to agree with other methods of experimental error propagation. So something like Bayesian methods, you can start getting agreement if you make this kind of modification. But it's complicated in order to do it. So you have to compensate quite a lot with the experimental distributions. And it feels kind of unsatisfying to be tinkering so much with this distribution.
Certainly, it's not very natural, certainly, in terms of the way that the way you deal with this problem, and it becomes worse as well when you get to the kind of level of data that we actually work with, which is instead of, so I've been describing it in terms of one data point and one theory parameter, and it's been fairly intuitive to kind of say we should put some more points when we don't have enough points there. It's way more complicated when you're fitting like a 700 dimensional space to like a 4,000 data points or something like that. And immediately your picture is you can't have a picture of it anymore. So it becomes immediately a problem that becomes a bit more intractable in terms of working out the correct way to fix the distributions to generate generate good results. But
for sure. And I guess the kind of computational effort required to just sort of trial and error that's going to grow quite immensely as well.
So the computational effort is a lot as it is, to be honest. So when we train one of our replicas, when we do the fit for a single replica, it takes about 10 hours of computing time, which is long, but it's not terribly long. It could be worse.
That's on a supercomputer, right? On a cluster.
That's right. It's on a cluster. Exactly. So therefore to do an actually do a realistic fit where you have a good number of replica universes, you need to do about 1,000 of those copies. So it's like 1,000 times 10 hours. You're looking at 10,000 computing hours really to do a single fit of your Poisson distributions. And then when you realize that you wrote the code wrong and then you have to submit the whole thing again, then you're like, then it rapidly becomes more than 10,000 hours. Already you're like doing trial and error in terms of changing the sampling distributions. It's not really a feasible attempt to fix the problem, unfortunately.
Campbell, you stole one of my questions.
Oh, I'm so sorry, Brian. I'm sorry. I'm too curious. Well, just to maybe steal another one. You've been talking about Bayesian methods, but that and trying to fit to those. I mean, that's sort of assuming, obviously, that those methods are providing a better handle on what the true error propagation is that we're looking for. I guess they might allow for a bit more insight into where our assumptions, where our assumptions come in when doing these calculations. But I mean, at the end of the day, there's no kind of fully independent check that we have, right?
That's completely correct. Yeah. So in terms of when we're trying to come up with these kind of error propagation methods, you do need to decide in terms of what you actually want to get out of this. So, and in a Bayesian method, the general idea is that you state your assumptions, and given the evidence, you will be able to infer the correct distribution. So and it's fairly basic probability theory. So you will be getting the correct answer in terms of the distribution that you get out if you already know what your prior knowledge is going to be. So people tend to tend to think that Bayesian methods are the kind of paradigm that you should be aiming for in terms of particle physics, and in physics more generally as well, because this is, as I say, reflects the kind of experimental process where you start with a hypothesis and then you test the hypothesis to get some more data on it, and you update your hypothesis accordingly. So this is different from the Monte Carlo, as I say, because the Monte Carlo is is really saying that if we repeated the experiment in multiple different universes, we would have this spread, but this is not something that you can do. You can only do the experiment once. So and this it puts Monte Carlo closer with what are called frequentist methods instead of Bayesian methods. And frequentist methods have this kind of this general idea that there is one truth, there is one 100% correct answer, and what my error bars should be, what my understanding of error bars should be, is that if I repeat my experiment a billion times, then I should get error bars for each of those different attempts, and on average 95% error bars, for example, 95% of the error bars will cover the true value. This is different from the Bayesian perspective, where actually the thing that you're hunting is really a random variable that gets updated in terms of its distribution every time you make an observation, and that distribution of the random variable becomes more and more precise as you hone in on the truth.
Right.
So the key difference is, as I say, Bayesian methods reflect the scientific process where you get more and more evidence, and you actually you carry on honing in on the truth. Frequentist methods, they're not quite in the same way, because they rely on the idea that you could repeat your experiment a billion times, which is not really the case. When we actually get when we get a result in particular in our field, we get a result from the LHC that tells us here is the result of proton-proton collisions, and this is the amount of proton-proton collisions that resulted in 2 double bosons being produced or something, and this is the number that we got, and here are the error bars, and we get nothing more than that, because you can't resolve it to okay, well those protons gave us that with that probability, and those protons gave us that with that probability. It's too coarse. It's too coarse in terms of the resolution that we have. So really, it's essentially we get one data point for it, and then there is no rolling the dice multiple times to check whether the kind of thing that we're computing is correct or not.
It's the philosophy is more about probability is meant to be telling us something about our degree of belief that we should have in a particular outcome or model or whatever, as opposed to frequentist, which it's saying something about the kind of long-term average of many repetitions.
That's exactly right.
I guess Bayesian would say something like, well, that's that's a rubbish model of probability or idea of probability to have, because you can't do these repetitions.
Exactly. Yeah. So I mean, and that is the case specifically in our field, and to be honest, in lots of other areas in physics as well. So yeah, but yeah, so often the frequentist kind of like mindset is not necessarily the appropriate one to be taking in terms of the error bars that you actually want to compute, and there isn't a guarantee that you are going to get the same answer either. So because the frequentist questions that you ask are they ask different questions to the Bayesian questions, despite the fact that superficially they can seem quite similar. Yeah. So as you say, degree of belief is different from like having long-term repetitions and things. Yeah. So they are subtly different ideas. Like even though you might expect initially for them to agree, but
yeah. I mean, that was going to be one of my questions. Is given that there are multiple methods, I guess I'm wondering, is there any virtue of maybe like a second level of analysis where, all right, maybe you've used your method and somebody else has done their method, and then is there a field where people look just at those and then try and combine them and say, well, we like your method 75%, we like this method 25, or at that point is it kind of just like, you're already spinning so many plates, and it's not. You
write the paper and be done with it.
It's difficult because there are plenty of error propagation methods within the field that I'm in. So, I mean, so as I say, the Monte Carlo replica method is the one that is used by the collaboration that we work with. But other collaborations do use different methods, and famously, the CTEC collaboration and the MSHT collaboration use something called the Hessian method for propagating errors, which is more Bayesian in its approach, but still makes lots of assumptions because it's quite difficult to propagate errors in such a high dimensional space. So you do even if you say I'm going to do a Bayesian method, you do have to kind of make some allowances to the fact that it's not easy to propagate the errors if you're not using this Monte Carlo, but the result of their fits, they obviously get fits as well, and they get error bars on those. All of them for the LHC are combined together by they combine the result of the NPDF determinations with the other determinations of the PDFs into one superset of PDFs, which are called the PDF for LHC sets. And so these are supposed to have some sort of not average, but some sort of representative weighting of the errors from each of the collaborations. So who say that the errors should look slightly different at different places, but so this is supposed to compensate for the fact that there is a variety of statistical treatments that go into these kind of determinations. Though of course it would be nice if there was one unified way of doing it. So unfortunately, every statistical technique suffers from limitations, definitely. So
cool. Yeah. Why is if there seems to be this kind of gold standard, if you like, of Bayesian methods, maybe that's too weighted, or that's too loaded of a term. But if people tend to like Bayesian methods or Bayesian methods of error propagation more, why what's the selling feature of Monte Carlo replica methods?
Well, the thing is, most of the time people expect good agreement between these methods. There are the kind of the pitfalls of Monte Carlo. It's quite difficult to see them a lot of the time because, as I say, when you're working with a 700-dimensional parameter space and a 4,000 data point set, it's not necessarily clear that these problems are going to manifest themselves. And the thing is, you in order to actually benchmark it, you need to compare with a Bayesian fit with exactly the kind of the same sort of settings, and that is also impossible to do because it's to do Bayesian methods you have to sample effectively from what's called the Bayesian posterior, which is this idea of this probability distribution that you get by updating your prior with the evidence. The Bayesian posterior, the resulting thing, it's not an object you can easily access. You have to somehow get sample from it. This is in contrast with Monte Carlo, where the data the data distribution is super easy to access. It's usually just a normal distribution distribution. You can just fluctuate easily. The Bayesian one, very difficult to access instead. And in order to sample from it, loads of methods have been developed. So things like Markov chain Monte Carlo, which is a different Monte Carlo. So it's a way of exploring the posterior distribution space. Right. But there's nested sampling, all sorts of like innovative methods to do it. But they typically only work very well in low-dimensional spaces. So people have to make approximations on what the posterior is going to look like, things like that. So if you want to benchmark the two against one another, you're going to struggle a little bit in terms of like saying, you know, like which one is whether Monte Carlo is doing a good job or not. But typically, the kind of approximations that people do with the Bayesian and the thing that people do with Monte Carlo, they typically agree pretty well. So, you know, like in terms of the stuff that people have, in terms of the PDF determinations that we currently have. The main problem with us is that the two methods disagree quite strongly when you start adding certain new physics effects in terms of the effective field theory that we were talking about before. So in one of the recent studies that we did, we tried to use Monte Carlo error propagation, and we found that it was telling us that there was a significant deviation from the standard model, like 4 sigma deviations for some of our operators, and you're like, these tiny error bands. And of course, you know, like we celebrated immediately, and we said, yeah, we discovered new physics, you know, like, but it turns out that, yeah, it was really kind of to do with this problem of, you know, like we were generating lots of replicas in the universes that were not well described by the theory that we were using. And the operators were trying to compensate with this, and they were getting highly peaked in a region where they really should have had much more of a spread. So cutting these replicas there really benefits it, and says, you know, like, yeah, actually there should be a bigger spread in general. But so it means that there's this subtle complication that sometimes you do have to worry about this. But yeah, cutting the replicas is also no easy feat, because it sounds like it's an easy job to do when you have, like, when I talked about the one parabola example, one data point thing, you can just say, get rid of the ones that fall below the parabola. But again, when you have a 700-dimensional space, 4,000 data points, it's very difficult to tell what regions are accessible by the theory and which ones aren't. So cutting it is a much more difficult problem than it seems initially. So yeah, but anyway, yeah.
And as you say, even if you do just cut them, you might get distribution, or you might get errors that also are not reflective of the true values.
That's also true. Yeah, exactly. So yeah, you do have to worry about like weighting factors and things like that. So so the problem is in general very difficult to solve. So yeah, so you kind of, when you're using the Monte Carlo, you just have to kind of hope that you're not going to be in that situation. So which is the majority of the hope with PDF fitting most of the time. You hope that the flexibility is going to be good enough to compensate, and actually it will give you some sort of reasonable distributions that should agree more or less with some sort of Bayesian approach. But yeah.
In your experience, is that a good hope, or is that too optimistic? Like, I mean, you had this one experience where things sort of led you initially to assume that you'd found some effect, but it turned out to be just sort of artifacts of these spurious replicas. Does that in practice happen kind of more than you would like, or is it actually quite a robust method in most cases in this effective field theory?
It's quite difficult to say, to be honest. So in a lot of determinations of these effective field theory parameters that we were talking about, the ones that are important for the new physics effects, a lot of the time the effect is not really highlighted, or at least to date it hasn't been. So yeah, but it turns out, but it can depend significantly on the data that you are including. So a lot of the time, or the theory that you're including. So if you the data that we were studying specifically recently was top quark data, where in top quark data, the like quadratic effects are really, really important, as it turns out. And so actually, it's not 100% the same, but it's like the parabola is like very, very sharply peaked. You know, like so it's very the quadratic really, really dominates basically. So yeah, you don't really get, you know, a nice like, you know, shallow decline. You know, like but yeah, so when we were doing our study, it became a really important effect. But in previous studies, actually, like they've not considered the same kind of data set, and as a result, they've not really seen the same sort of effect. But yeah, one of the collaborations that do fitting exclusively of the EFT parameters, so the ones that just describe the new physics, who don't fit the PDFs at the same time, they just fit the EFT. They assume like standard model PDFs, so which is a bit of assumption in itself. But they benchmark everything. They benchmark the Bayesian against the Monte Carlo, and they find very good agreement in all the data sets they consider. But when we get to the kind of the top data set that we've been considering, then actually they do start seeing disagreement in their method as well. So so it really can highly depend on the data set that you're using. So in terms of PDF fitting as well, which is one of the things that obviously we're concerned with a lot, it's difficult to say, a lot of the time. I mean, in most PDF determinations that we've had so far, the error bars seem to agree quite nicely across, the methods that other collaborations use, which are only approximately Bayesian compared with ours, which is Monte Carlo. But we don't really know if anyone has checked, on the most up-to-date data set, whether, Monte Carlo is doing a good job compared to, a Bayesian method. And we don't know if anyone has checked, on a proper Bayesian fit, not one that's just approximate, whether they're getting the same sort of answers. Indeed, actually, there was a recent determination by the NMPDF collaboration of PDFs, I think at the end of 2021. Their latest publication was that they found that actually they have very small uncertainties now with the new data set that they have. And a lot of people were not really expecting these small uncertainties, and a lot of people were saying, "Oh, the uncertainties are a bit too small." I don't know, we're compared to some of the other groups, you're getting very small uncertainties, and we don't necessarily trust these so much. And we think that one of the explanations could be to do with this Monte Carlo, but and that's something that we're thinking about at the moment and trying to have a look at, which is obviously an important thing because people do use these PDFs, as I say, in the LHC predictions in general.
Yeah.
But yeah.
Yeah. I was very facetiously going to suggest calling this episode something along the lines of "Is most particle physics wrong?" or something. I don't know what we're going to end up calling it, but I guess it's. But the answer obviously to that question is I'm sure no. It probably is correct, but the question of when, to what degree we can say it's correct is quite a subtle one.
Exactly. Yeah. So I mean, when we kind of get down to the the small uncertainties that we have on these PDFs, it can be we're at kind of the level where most people agree that the PDFs are pretty good, they're doing a pretty good job. Yeah. But at the small level of uncertainties that we're at now, we're kind of in a very precision era of physics when it is important to get this kind of detail right. So if you go back 20 years, no one cared. I don't know, and if you go back 40 years, no one had any errors on these parton distributions anyway, and they were like, someone will work that out eventually, I'm sure. So and they didn't even take it into account as an effect that was an error. But now it's actually becoming important, and it probably is important to get these subtle effects right. But will getting the subtle effect right, I don't know, suddenly change our entire outlook on particle physics? No, it won't. But it will contribute to a better precision physics program, which of course is important when we're hunting for new physics. So we don't want to suddenly claim the existence of new physics when it isn't really there. It's just our poor statistics. Yeah. So
right. Which, I mean, has kind of happened in the past, hasn't it? In the not so distant past, there have been sort of news headlines that there might have been a new particle discovered, new force discovered, something like that.
Exactly.
And it was never sort of 5 sigma, right? It was that's a sort of indication that there might be new physics, and then you do a bit more analysis and the effect goes away.
It's true. Yeah, you can get very excited by some headlines sometimes. You're like, maybe something's happening, and then you find out very shortly that someone has done some maths wrong, and actually it's not quite right.
Yeah. Damn, standard model is so good.
It's very robust. Yeah.
For any of my students listening, check your work.
Yeah.
I always say check your work.
True. And those error bars you draw on the graphs, they're very important.
They are. So, it's the sort of thing that, when I was at school, I was like, why are we doing this? But no, it turns out to be very, very important in the long term. But But of course, and it is important to say everyone makes mistakes, including, physicists who work for the LHC. So, but I don't know. But usually the result is, we make an approximation and we realize that the approximation is actually not so good, or the methodology is not so good, and actually it needs to be refined in some way to get the kind of level of precision that we would like to have. So that's probably a fairer way of saying it, rather than saying that everyone is just bad at statistics or something.
I mean, audaciously, I might claim, right, that it doesn't actually matter if there's a mistake on an individual paper or an individual person makes a mistake, because the whole point of science, right, is that you sort of take the wisdom of the crowd, and you look at the consensus of the field over many repetitions of the experiments and much analysis of the data, and we've got a pretty good understanding of particle physics from many years of smashing particles together.
I absolutely agree. Yeah.
Brian, do you have any other sort of concluding questions or remarks?
I do not.
Well, I feel like that's a fairly good place to wrap up. Unless there's something else that you feel like you just have to get off your chest, James.
No, I think that's it. Yeah. So thanks very much for listening to me talk about dry statistics for 2 minutes.
That was fascinating. I mean, like who knew that the sort of philosophy of probability had so much to do with looking for, beyond standard model physics. It's pretty cool. Well, I mean, thank you again very much for joining, James, for 2 whole episodes, taking up a lot of your valuable 4th-year PhD thesis writing time. Sorry about that.
No, you're very welcome. Anytime.
Thanks again to Andrew for the suggestion of the topic and the question.
Yeah, thank you everybody for listening. As always, sharing, rating, reviewing helps. More data points, essentially. The more reviews we have, the more ratings we get, more data. Everybody will have a better understanding of where we are at in the physics podcast landscape. I just want to add my own thanks to Andrew and to James. James, anytime you want to come back, the space is yours. You want to go off on some new method of statistical analysis? Here's your platform. So
thank you. Thanks.
I know. There's not a lot of places make space for that, but here on Question Field, No, thank you so much.
Anytime.
Yeah, and we'll see everybody next time.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars located in the review section of your favorite podcast app. Thank you for listening.